The universe is a colossal puzzle, composed of an infinite number of pieces. We see only a tiny fraction of them, and can only guess at the rest. The cosmic abyss conceals an enormous number of secrets and mysteries, and we have yet to unravel them. But today, let's embark on a fantastic journey through the expanse of the universe, and touch upon the most fundamental foundations of its existence. What if I told you that a butterfly's wings in Brazil could trigger a hurricane in Indonesia? What if the sentimental memories of a honeymoon saved an entire city from nuclear annihilation? What if the universe itself was born from chaos? Not the chaos of disorder, but something far more profound and mathematical. We're going to plunge into the depths of primordial chaos to understand how cosmic order emerges from it. We'll explore why the universe seems impossibly fine-tuned for our existence. We'll confront the terrifying question, why haven't we heard from other civilizations? Are we alone in the universe? Or is some invisible barrier, preventing intelligent life from reaching the stars? And then we'll venture to the very end, to the death of everything, to a time so distant that stars themselves will be ancient history, when the last light fades from the cosmos and the universe faces its final moments. This is a journey from the butterfly effect to the heat death of reality itself. Are you ready? Let's begin. Kyoto, Japan, 1893. A young lawyer named Henry Stimson and his wife Mabel White are spending their honeymoon in this ancient city. They're enchanted by the Eastern culture, the temples, the gardens. It's a journey they'll remember for the rest of their lives. Fast forward 52 years. Los Alamos, USA. May 11th, 1945. A special committee of the U.S. Army is compiling a list of priority targets for atomic bombardment. At the top of that list sits Kyoto, the country's largest industrial center. But then something extraordinary happens. Secretary of Defense Henry Stimson, the same man who honeymooned in Kyoto half a century earlier, personally crosses the city off the list, citing its high cultural significance. Hiroshima becomes the primary target instead. The next target, the city of Kokura, August 9th, 1945. Japan. The crew of a B-29 bomber receives critical orders. The military arsenals in Kokura must be obliterated. They're carrying a bomb of unprecedented power, a weapon that will change history. But when they arrive, thick fog blankets the city. The crew can't see the target. Commander Charles Sweeney makes a decision. They'll proceed to the secondary target, Nagasaki. Think about this for a moment. Sentimental memories from a honeymoon 50 years ago and an ordinary weather phenomenon changed the fate of millions of people. 2 cities lived, 2 others didn't. This isn't just a story about war. It's a story about something deeper, something that connects butterflies and hurricanes, tiny decisions and cosmic consequences. It's about chaos. A mathematician and meteorologist named Edward Lorenz is trying to predict atmospheric behavior using computer modeling. He believes that with new computational power, he can forecast weather with unprecedented accuracy. But the results perplex him. To speed up calculations, Lorenz breaks the process into stages, with the final results of each becoming the starting conditions for the next. The computer rounds some numbers slightly. Changes so small they shouldn't matter. Tiny fractions of a percent. But they do matter enormously. The continuous calculation and the step-by-step calculation produce radically different results. The same equations, the same starting point, completely different weather patterns. Searching for answers, Lorenz discovers something remarkable. All possible solutions cluster around 2 positions he calls attractors. When you plot each solution as a point in 3-dimensional space, They form a shape that looks like butterfly wings. And here's the crucial part. The tiniest change in any starting parameter can violently shift the final result from one wing to the other. This becomes known as the butterfly effect. But it's only one piece of a much larger theory: chaos theory. Actually, Lorenz wasn't the first to notice this phenomenon. German philosopher Johann Fichte and French mathematician Henri Poincaré had expressed similar ideas decades earlier. But Lorenz transformed an annoying computational error into a powerful theory capable of answering profound questions. Here's what makes chaos different from randomness. Chaotic systems follow perfectly clear, understandable laws of physics. But those laws are so complex that the system's behavior appears unpredictable. That's why they're called deterministic chaos, predetermined yet seemingly random. If you observe a chaotic system multiple times with absolutely identical starting conditions, it will always behave identically. But a truly random system will give different results every time. Radioactive decay, for instance, is genuinely random. We can calculate roughly how many atoms will transform in a sample, but we cannot predict when a specific atom will decay. That's pure chance. Chaos is different. Chaos has rules. The mathematical definition of chaos requires three key properties. First, the system must be nonlinear. This means that the whole is not simply the sum of its parts. Push a linear system twice, get twice the response. But push a chaotic system twice, you might get 10 times the response, or half the response, or something completely unexpected. Second, the system must be sensitive to initial conditions, the butterfly effect. An imperceptibly small change at the beginning can send the system down a completely different path. Not just a slightly different path, a completely different one. Third, different parts of the system must intersect and interact. Classical physics often ignores these interactions to simplify calculations, but that's usually too crude an assumption. These complex, multifaceted influences make chaos theory models so complicated and so realistic. Now here's where it gets cosmic. Let's travel back 13.8 billion years. The Big Bang just happened, or more accurately, it's happening right now, in the first quantum moments of time. There's no matter or energy as we understand it. The four fundamental forces haven't separated yet. They're bound in a single, incomprehensible force. The physical laws we know don't work yet. But other rules, equally strict, equally unforgiving, are determining the future development of the system. And here's the thing. The tiniest change at any point in the nascent universe could have completely altered its future. A quantum fluctuation here, a random variation there, each one cascading through time, magnifying, multiplying, creating. Our reality was literally born from chaos. Mathematical, deterministic, beautiful chaos. Now imagine, about 1 million years have passed. Space looks more familiar now, but there are no stars yet. No planets, just endless clouds of primordial hydrogen filling the young universe. Gravity compresses the hydrogen, creating centers of attraction that will soon become the first stars. These protostars are massive enough to gravitationally influence each other. Move any protostar sideways, change its mass slightly, and the changes will affect not only its own developmental path, but those of its nearest neighbors. Chaos continues to rule. Over the next billions of years, those first stars burned and exploded, enriching the universe with heavier elements. New stars formed from hydrogen clouds, while cosmic dust swirled into giant vortices around them, forming protoplanetary disks. The familiar pattern, chaotic movement and interaction, creating order from disorder. About 4.5 billion years ago, our solar system was born from this cosmic dance. But here's what blows my mind. Why this solar system? Why these conditions? Our sun, A yellow dwarf giving us light and warmth every second sits on the outskirts of the Milky Way, orbiting the galactic center beneath something called the corrotation circle. What does that mean? The sun's speed precisely matches the rotation of the galaxy's spiral arms, regions of active star formation. Because of this amazing synchronicity, our solar system almost never crosses the arms, avoiding deadly supernova explosions and proximity to hot, active stars. The diameter of this galactic orbit also matters tremendously. If the sun were closer to the galactic center, the abundance of heavy elements would make forming planets too large and massive. Plus, powerful ionizing radiation from the galactic core would sterilize any attempt at life. But move too far from the center, and the diversity of chemical elements drops sharply. Rocky planets with varied compositions like Earth couldn't form. We'd be surrounded by gas and ice giants at best. Inside our solar system, the coincidences multiply. Earth sits at the perfect distance from the sun, rotating in a stable orbit with low eccentricity, almost a perfect circle. Change its diameter by just 5% in either direction, and our planet becomes either ice-covered or shrouded in water vapor. Either way, complex life ends. The sun itself has critical properties: not too hot, not too cold, with a long lifespan. Hot stars create wider habitable zones but burn out quickly and emit excessive radiation. Cooler stars, like red dwarfs, have narrow habitable zones so close to the star that planets often become tidally locked, creating extreme temperature differences. But here's what really haunts me. These aren't just lucky breaks for Earth. The entire universe seems fine-tuned for our existence. Consider this. Only in three-dimensional space can stable orbits exist for celestial bodies. In universes with more or fewer dimensions, electron orbits in atoms become unstable. Electrons either inevitably fall into the nucleus or fly off into space. Atoms can't exist. A universe with different dimensions would contain only radiation and scattered elementary particles. No atoms, no chemistry, no life, and it gets stranger. All modern physics rests on several fundamental constants: the speed of light, the gravitational constant, Planck's constant, elementary charge, and the masses of electrons and protons. We've measured these experimentally, but we have no idea why they have these specific values. Here's the terrifying part. Change any of them slightly, and the universe becomes lifeless. A free neutron is slightly heavier than a system of a proton and electron. If this inequality didn't hold, hydrogen couldn't exist. Its atom would instantly transform into a neutron. Without hydrogen, no stars. Without stars, no heavier elements. No chemistry. No us. If the coefficients of Coulomb force and strong interaction differed even slightly from current values, thermonuclear fusion in stellar cores would be impossible. Increase the gravitational constant, and you get massive, hot stars with short lifespans that collapse into black holes, and neutron stars, locking away most universal matter forever. Decrease it, and gravity can't compress gas clouds enough for fusion to ignite. No stars, just giant brown dwarfs. Change the electromagnetic interaction in any direction, and chemical reactions become impossible. Complex compounds can't form. Increase Coulomb force too much, and no elements heavier than boron could exist. Electromagnetic repulsion would tear their nuclei apart. The formation of heavy elements in the universe requires a precise combination of factors. Only because of a special state of carbon, called carbon resonance, can helium transform into carbon. This phenomenon plays a crucial role in heavy element formation and distribution throughout the universe through supernova explosions. And carbon is essential for life. Only carbon can form long, branched chains, providing the foundation for an incredible diversity of chemical compounds. Life as we understand it is only possible based on organic compounds, which are unthinkable without carbon. So here we are, surrounded by impossible coincidences. The universe seems designed for us. But by whom? Or what? This cluster of amazing coincidences gave birth to the anthropic principle. Though the term appeared only in 1973, the underlying idea surfaced much earlier. Soviet scientist Grigory Idlis wrote in 1958, "We observe not an arbitrary region of the universe, but that special structure which made it suitable for the emergence and development of life." This is called the weak anthropic principle. Later came the strong anthropic principle, which states the universe must have properties allowing intelligent life to develop. Or put another way, for the universe to exist, an observer is necessary. This last formulation relies on the important role of the observer in quantum physics. Their presence radically changes particle behavior. The observer is always an integral part of the experiment. You can also phrase it this way: the laws of our universe are what they are because only in such a universe can we exist. The anthropic principle implies that other universes, or regions of a single universe with different physical laws, might theoretically exist. But either humanity can't observe them, or these hypothetical worlds don't achieve reality because they lack an observer. This can develop into multiverse theory, or the hypothesis that basic physical constants might change over time. However, observations of the accessible part of our universe show that fundamental constants don't change with time, and the multiverse concept can't be described scientifically. Stanisław Lem commented, "This is an attempt to explain the unknown through the unknown." The anthropic principle also contradicts the principle of mediocrity, which states that the region of space accessible to humanity isn't unusual, and many similar places exist within the universe. The Milky Way has no unique structural features. Its position in the universe's large-scale structure doesn't stand out among billions of other galaxies. Moreover, modern physics accepts the principle of space homogeneity. The laws of nature remain the same at every point in the universe. Numerous observations confirm this postulate, so we're left with a haunting question. Is the universe fine-tuned for us? Or did we simply arise in the one universe where life was possible? Are there countless dead universes we can never see? Or, and this is the darkest possibility, are we the only ones? Are we alone, not by cosmic bad luck, but because something stops civilizations from reaching the stars? Something called the Great Filter. Imagine the Milky Way contains 400 billion stars. Conservative estimates suggest trillions of planets. Many should be inhabitable zones. Some should have developed life. Some of that life should have become intelligent. Some of those intelligences should have developed technology. Where is everyone? This is Fermi's paradox, and it haunts every astronomer who's ever pointed a telescope at the stars. We should see evidence of alien civilizations everywhere. Radio signals, megastructures, probe fleets, something. The galaxy is 13.8 billion years old. If technological civilization arose even once before us, they've had millions or billions of years to spread across the stars. Yet we hear nothing. Absolute silence. In 1996, economist Robin Hanson proposed a chilling explanation: the Great Filter. The idea is simple and terrifying. Somewhere between the first replicating molecule and a galaxy-spanning civilization, there's a barrier, a filter. A step so incredibly unlikely or difficult that almost no one passes through it, and we don't know where it is. Think about the path from primordial soup to starship. First, a planet must form in a habitable zone. Then life must begin, abiogenesis, the transformation of non-living matter into living matter. That life must develop reproduction using molecules like DNA and RNA. Simple cells must evolve into complex ones. Multicellular organisms must develop. Sexual reproduction must emerge, vastly increasing genetic diversity. Complex organisms must learn to use tools. Those tool users must develop technology. That technology must enable space colonization. The civilization must colonize other worlds and star systems while avoiding self-destruction. That's a lot of steps. And according to Hansen, somewhere in there is a filter so difficult that it stops almost everyone. Here's the nightmare. If we haven't encountered the great filter yet, it's ahead of us. The easier evolution on Earth has been up to now, the worse our chances in the future. If we breezed through the early steps, then the hard part, the killing part, is still waiting. Some researchers interpret our apparent cosmic loneliness as good news. Maybe the great filter is behind us. Maybe the really hard part was getting from chemistry to intelligence, and we're among the few who made it. But what if we're wrong? Consider, we're already capable of destroying ourselves through global thermonuclear war. We're developing artificial intelligence without fully understanding it. We're altering our planet's climate. We're creating biotechnology that could engineer pandemics. Any of these could be the filter. And maybe, just maybe, this is why the universe is silent. Maybe civilizations routinely destroy themselves right around our current level of development. Maybe the great filter isn't some mysterious cosmic phenomenon. Maybe it's just us. Maybe intelligence inevitably creates the tools for its own destruction, and very few species are wise enough to survive their own success. The discovery of simple extinct life on Mars would be terrible news for humanity. It would mean life emerges easily. The filter is ahead. The discovery of extinct complex life would be catastrophic. It would mean the filter is very close. But the silence, the cosmic silence, might be the worst news of all, because it suggests that something, somewhere between where we are now and star-faring civilization, almost nobody makes it through. Are we doomed to join the silence? Or are we somehow going to be different? But let's imagine, just for a moment, that we make it through, that we overcome whatever barriers lie ahead, that we don't destroy ourselves, that we solve the energy crisis, that we build ships capable of crossing the terrible distances between stars. What would that take? The distances of space are crushing. With our best modern engines, reaching the moon takes weeks. Getting to Mars along the most optimal trajectory requires over half a year. The legendary Voyagers, after 45 years of flight, have barely left the inner solar system. They'll spend the next several millennia traveling through the scattered disk and hypothetical Oort cloud. The fastest spacecraft right now is the Parker Solar Probe, which will reach a record 194 kilometers per second by 2025, but only thanks to the sun's gravity. It can never leave our star's vicinity and is doomed to eventually burn in its photosphere. Chemical rocket engines have exhausted their development potential. They're not suitable for interstellar journeys. Alternative concepts exist: nuclear pulse propulsion, solar sails, but their implementation faces serious obstacles. And there's another critical problem: energy. Long-distance flights demand stable, powerful energy sources. All current spacecraft have relatively small sizes and limited power supplies. Autonomous probes typically use isotope batteries that inevitably degrade. The Voyagers have almost all systems unpowered now, drifting on inertia. The ISS and orbital stations combine solar panels and radioisotope thermoelectric generators, but most power goes to life support, with ion drives only for orbital correction. A prolonged crewed flight to a distant planet or star would require far more energy. And here's the problem: 99% of the path to another star, passes through interstellar space, devoid of obvious energy resources. Even the brightest stars' radiation noticeably weakens across cosmic distances. For journeys to other worlds, we need an autonomous, powerful, and ideally inexhaustible energy source. Could we find it in the structure of the universe itself? In the quantum foam of spacetime? Scientists from Princeton and Hong Kong create an incredible device that appears to violate fundamental physics laws. A microscopic mechanism consisting of two silicon gear plates, 100 nanometers apart, can generate small amounts of energy literally from emptiness. This should brutally violate conservation of energy, one of the foundational principles of the universe. But it doesn't. The device exploits the Casimir-Polder effect, discovered mid-last century. In its simplest form, if you place two thin plates in a vacuum at very small distances, they'll attract each other. This phenomenon is intimately connected to Heisenberg's uncertainty principle, which implies the existence of zero-point vacuum fluctuations. Virtual particle pairs constantly appear everywhere in the universe, essentially from nowhere, but their lifetime is only 10 to the power of minus 23 seconds before they disappear back into non-existence, restoring balance. In open space, virtual particles with any parameters are generated, but between the plates, only those with strictly defined wavelengths can exist. More numerous external particles press on the plates more strongly than internal ones. You can imagine the space between plates having negative pressure, as if we pumped even more out of the vacuum. This mechanical tension can be transformed into electrical current. The Princeton and Hong Kong researchers did exactly that. The current is small, but the principle matters. Energy flows into our world practically from emptiness. And here's what's extraordinary. From the Casimir effect flows the Scharnhorst effect. Calculations suggest that between these plates, the speed of light should exceed the familiar 300,000 kilometers per second, because photons don't collide with virtual particles. Current technology can't yet test this experimentally, but the mathematical justification leads to far-reaching conclusions. The famous theoretical faster-than-light engine project, the Alcubierre drive, received proof of potential feasibility thanks to scientists from Baylor University, Gerald Cleaver, and Richard Obosi. They combined quantum field theory equations with general relativity, obtaining complex but clear justification for the bold concept. According to quantum field theory, space has not 3 dimensions but many more, noticeable only at the microcosm level. Applying this theory's equations to calculate the Casimir effect, researchers concluded that with powerful energy impact, you can control its properties. Compress space behind a hypothetical starship and make it more rarefied ahead, and you create a region like an Alcubierre bubble, capable of moving at faster than light speeds. This doesn't violate relativity. The ship doesn't move. The space around it does. The main problem was always the incredible energy required, converting an entire planet into radiation just to form a bubble that could contain a starship. But if researchers can scale Casimir effect generators to necessary power levels, we could obtain energy anywhere in the universe, literally from emptiness. Of course, a functional starship requires solving many more problems. Space isn't the most favorable environment for humans. It's permeated with deadly radiation that destroys living cells and provokes harmful mutations. Protection requires thick metal shields or magnetic fields with specific parameters. Random collisions with micrometeorites and cosmic dust pose another threat. At high speed, even tiny grains possess incredible kinetic energy and can punch through metal plates. In a long interstellar journey, repair capabilities are extremely limited, and a hull breach could be fatal. Plus, long expeditions without Earth support require creating a closed biosphere within the starship. Scientists from various countries are working in this direction. The ISS has been growing various plants for many years, both for scientific purposes and consumption. Engineers are developing waste processing and life support product purification systems, but we're still very far from creating a full orbital ecosystem. Let's imagine we solve all these problems. We build the ships. We find the energy. We venture into the darkness between stars. What would we find? Our solar system is just one of countless planetary systems in our galaxy. It includes a single main sequence star and 8 planets with their moons. The system also contains over 1 million small celestial bodies, asteroids, comets, meteoroids. The farthest known planet is Neptune, whose orbital radius is about 30 astronomical units, or roughly 4 light-hours. But amazingly, inside Neptune's orbit lies only a tiny part of the solar system. The most distant discovered object is called Farfarout, currently about 132 astronomical units from the Sun, 18 light-hours. Yet even this celestial body, barely visible against the cosmic abyss, is nowhere near the hypothetical Oort cloud. The cloud's inner boundaries lie approximately 2,000 astronomical units from our system's center, with outer boundaries stretching to at least 60,000 astronomical units, about 1 light-year. These frontiers define the limits of our Sun's gravitational influence. Beyond lies interstellar space. Continue outward, and within 20 light-years from the Sun, you'll find over 50 diverse stars, from dim, cool brown dwarfs to bright, well-known objects like Sirius, Procyon, or Altair. Some have planetary systems containing worlds potentially suitable for life's emergence and development. For instance, Gliese 832 Psi-c, about 16.1 light-years from the Sun, resembles Earth more than any solar system planet. Average surface temperature reaches 253 Kelvin, with a full orbit taking just 36 Earth days. By universal standards, the distance is relatively small, but a spacecraft leaving our system at 17 kilometers per second would need about 300,000 years to reach Gliese 832 C's vicinity. Building an interstellar ship capable of enduring such a long journey remains impossible at our current technological development stage. Our solar system and stellar neighbors belong to the Orion Arm, which is part of the Milky Way galaxy. It contains about 400 billion stars, around which calculations suggest over 1 trillion exoplanets of various types might exist. The Milky Way's main diameter spans about 100,000 light-years, with the stellar halo potentially reaching twice that size. The main disk's thickness is roughly 1,000 light-years, though the galactic center has a noticeable bulge called the bulge, with a cross-sectional size around 3,000 light-years. The Milky Way belongs to the local group of galaxies, an extensive structure including over 50 galaxies concentrated in a space region about 10 million light-years in diameter. Andromeda, Triangulum, and the Milky Way are the largest. Total cluster mass may approach 3 trillion solar masses, mostly from our galaxy and Andromeda. About 2.5 million light-years separate us from Andromeda, making it the closest galaxy to us. The local group is part of the gigantic Virgo supercluster, consisting of over 30,000 galaxies located in a cosmic space region about 150 million light-years in diameter. Its total mass reaches about 1 quadrillion solar masses, approximately 1,000 Milky Way-sized galaxies. The supercluster has a flattened shape. About 60% of all constituent objects can be represented as a flat sheet roughly 10 million light-years thick. Enormous, yet quite small by universal, large-scale structure standards. Gradually pulling back, we'd see a giant galaxy supercluster about 520 million light-years across, called Laniakea, including several galactic superclusters, including Virgo supercluster and the Great Attractor. Total mass exceeds the Sun's by about 100 quadrillion times. The Great Attractor, located approximately 250 million light-years from Earth, serves as a center of attraction for all nearby objects. Direct observation from Earth is impossible because the Milky Way's plane blocks instruments. The Great Attractor's nature remains an unresolved mystery. Laniakea is part of the universe's large-scale structure, a complex system of galactic filaments, walls, and voids. Some structures have truly unimaginable sizes. For example, the Hercules Corona Borealis Great Wall stretches about 10 billion light-years. Discovered in 2013, this superstructure is considered the most gigantic component of the universe's large-scale structure, containing probably millions of galaxies. Counting the exact number of constituent stars is likely impossible. This structure's very existence puzzles science. According to currently accepted universal evolution theory, forming such gigantic clusters is simply impossible. Yet this wall, which the human mind cannot fully comprehend, occupies only a tiny fraction of the visible universe. According to modern cosmological understanding, our universe's space constantly expands. Expansion speed depends on distance between objects. The farther apart, the faster the distance grows. This removal isn't limited by light speed, because space's fabric itself expands. At a certain distance, objects become mutually invisible. Observations of cosmic microwave background radiation show that the observable universe region forms a sphere about 93 billion light-years in diameter. According to relativity theory, we can see and interact only with objects inside it. This space section is called the metagalaxy, which could be either the entire universe or a small part. Hypothetically, beyond the visible cosmic space region, unknown structures might exist. Such entities are called extra-metagalactic objects. Unfortunately, studying them scientifically is currently impossible. Nevertheless, some astronomical objects at the visible universe's boundary move unlike they should according to available data. Such anomalous movement cases might prove that beyond the metagalaxy, massive structures might exist. Their gravity permeates surrounding space, influencing nearby objects. Many hypotheses exist about the universe's structure beyond the metagalaxy, but most have more metaphysical character. For instance, one viewpoint suggests that beyond universal boundaries, time and space don't exist in our familiar understanding. Known physical laws don't work, and concepts like matter, substance, or energy become meaningless. Logical development of this hypothesis leads to multiverse theory, or the hypothesis that basic physical constants might change values over time. But observations of our accessible universe show fundamental constants don't change with time, and multiverse representation can't be scientifically described. Some anthropic principle interpretations suggest that beyond the visible universe, other worlds exist with different fundamental constant values, like light speed or electron charge. This closely relates to multiverse ideas, which can be represented as foam, consisting of many bubbles, separated by thin but insurmountable partitions. Thus, each universe represents separate space with its own physical laws, possibly fundamentally different from those we're accustomed to. The most radical hypotheses deny our world-objective reality. According to these assumptions, the universe represents only simulation similar to computer virtual reality of incredibly high level. Typically, such ideas assume that beyond our familiar reality exists some super being or super civilization whose development level far exceeds ours. Their goals and capabilities are probably mysterious and incomprehensible, but proving or disproving such hypotheses is likely impossible. Let's talk about the end. Famous American writer Ursula Le Guin once wrote through a character's voice, "For a word to be spoken, there must be silence before the word and after it." She was talking about the birth and death of all things. Every object in the universe has a beginning and an end. Some elementary particles exist for barely measurable fractions of seconds. Microorganisms live from hours to days. Humans live for decades. Even stars, which can shine for millions or billions of years, eventually fade. But what about the universe itself? Will it die too? And if so, how will it happen? What comes after? The earliest theory was the steady-state universe. Our universe had no beginning or end, always existed, and would exist eternally in equilibrium and stable condition. But observations and calculations quickly showed this unlikely. Irreversible processes exist in the universe. In the 1910s to 1920s, the theory we now call the Big Bang began forming. Currently, it's the most developed scientific theory explaining the universe's origin and evolution. Dozens of scientists contributed, with Albert Einstein's work on general relativity providing the foundation. The main conclusion: the universe's fate depends on dark energy, a theoretical energy type causing space expansion. But nothing definite can yet be said about this physical phenomenon's essence. Many theories exist, each with advantages and disadvantages. According to current data, the universe's age counts from the Big Bang moment, just under 14 billion years. The universe constantly expands, and depending on dark energy density, it will either eternally expand at ever-increasing speed, or expansion will gradually slow and reverse. In this case, the universe will compress back into infinitely small singularity, similar to its birth. Current science can't give a definitive answer. Which possibility is more likely? Two equally probable development scenarios emerge: the Big Rip and the Big Crunch. The Big Rip, universal expansion speed, depends on distance between objects and occurs faster the farther apart they are. Imagine an air balloon with two dots marked on it. As you inflate it, those marks move apart. That's roughly how universal expansion works. Space itself expands. The farther dots are initially drawn, the faster they separate. At sufficient distance, this speed exceeds light speed. This threshold is called the event horizon. All objects beyond it disappear for the observer. Impossible to interact with, impossible to observe. Just imagine. First, distant galaxies and clusters will vanish from the sky. Then one by one, Milky Way stars will fade, starting with the most distant from the Sun. If the Big Rip theory is correct, universal expansion speed will constantly increase. This will lead expansion forces to gradually overcome gravity. First, galaxy clusters will disintegrate, then galaxies and star clusters themselves. Then star systems will fall apart. Stars can no longer hold rapidly fleeing planets and moons. The next stage, matter decomposing into atoms, then atoms into elementary particles. Matter will cease existing. After this, modern physics laws will stop working, and what happens next is unpredictable. The Big Crunch. Current observations show space expands and expansion speed increases. But we know nothing about dark energy's essence, so the process might reverse. The universe might begin compressing. For instance, this could happen if total gravity created by all universal matter exceeds expansion force. This event scenario is called the Big Crunch. In this case, universal processes will proceed roughly as now, until size decreases about 5-fold from current. Galaxy clusters will merge into one supercluster, occupying the entire universe. But within galaxies, stars will still be born and die. Planets will form, and other events will occur. When the universe compresses another 20 times, volume reaching just 1% of current, all galaxies will merge into one. Cosmic microwave background radiation temperature will reach 274 Kelvin and continue rising. This means soon, liquid water necessary for biological life won't remain anywhere in the universe, at least in our familiar form. Further space compression will lead to even greater universal heating. Planets will be scorched, then melted. All matter will be crumpled into an enormous cloud of boiling plasma. Then atoms will decompose into parts, elementary particles. Eventually, the universe will compress into singularity, similar to its birth. There's also the theory of the Big Bounce, development of Big Crunch theory. According to it, after the universe collapses into singularity from Big Crunch, it will be born again in another Big Bang. These events will occur again and again, presumably eternally, as far as one can speak of eternity beyond space and time. It's hard to say how long any of these scenarios would take. Too little is known about dark energy. Maybe the Big Rip or Big Crunch will occur while stars and planets still exist. But what if not? What if the universe's final death moment is very distant in time? Physical laws dictate that our familiar universe can't exist infinitely. 4 extended cosmological epochs are distinguished, each with its own character. The Stelliferous Era. We live in what's called the Stelliferous Era, the Age of Stars. In our surrounding universe, abundant interstellar gas reserves remain, raw material from which stars form. New stars continue being born, and this process won't end until all interstellar gas is exhausted. This era will end in 1 to 100 trillion years. During this time, the Sun and the absolute majority of other stars will exhaust nuclear fuel reserves and transform into white dwarfs, neutron stars, or black holes. The Degenerate Era. The next epoch is called the Degenerate Era. By this time, main sequence stars will no longer exist. Most universal matter will concentrate in white and brown dwarfs, leaving little to neutron stars and black holes. All these objects will slowly cool over very long periods, about a duodecillion years. White dwarfs will gradually release accumulated heat through radiation and transform into black dwarfs. Brown dwarfs will also cool, and sluggish thermonuclear reactions in their cores will finally cease. Gradually, most matter will be absorbed by black holes. At this developmental stage, main processes will be dark matter annihilation and proton decay. Protons, elementary particles composing all known atoms, are considered among the longest-lived elementary particles. Calculated proton lifetime is about 100 duodecillion years. Thus, by the Degenerate Era's end, universal matter should represent a sea of scattered elementary particles, among which remain isolated neutron stars and black holes. The Black Hole Era. The next epoch is called the Black Hole Era. According to some theories, they'll gather into clusters, merging with each other until forming a single, giant black hole. According to other theories, black holes will slowly evaporate, radiating energy until finally disappearing. Black hole evaporation is a quantum effect caused by Hawking radiation. It proceeds more intensely the smaller the black hole, and ultimately deprives the whole of all its matter and energy. This process will finish presumably in 10 to the power of 100 years. This number is called a googol. Either way, eventually the universe will contain only dead space filled with residual products from previous era processes: photons, electrons, positrons, neutrinos, and quarks. Electrons and positrons will gradually annihilate each other. In this form, the universe theoretically could exist indefinitely long, at minimum, until Big Crunch or Big Rip. The Dark Era, in any case, humanity won't survive to this moment. Most likely, it will disappear still in the Stelliferous Era. Our planet will be suitable for life about another billion years. Then it will be scorched by the gradually heating sun. In 5 to 6 billion years, our star, having become a red giant, will shed outer shells and transform into a white dwarf. But what will happen after the universe's death? The answer to this question is hardly possible. After the universe's death, by whatever scenario it occurs, there will be neither space nor time in accessible understanding. Even if the Big Bounce theory is correct, and after Big Crunch there'll be a new Big Bang and new universe with its galaxies and stars, we'll never learn of it. Just as we can't learn of the previous universe, the one before ours, because for a word to be spoken, there must be silence before it and after it. The universe consists of countless objects connected by inexorable physics laws. While in one part, celestial bodies circle their stars for billions of years in measured rhythm, in others, blinding flashes incinerate entire star systems in mere seconds. We see only a small part of the cosmos's incredible diversity. In its depths lurk many more great secrets and mysteries, which means we'll make many more fantastic journeys into the universe's depths. From chaos theory to the anthropic principle, from the great filter to the heat death of reality, from the first stars to the last black holes, from the butterfly's wings to the end of everything. We are the universe trying to understand itself. We are matter that became aware of matter. We are chaos that discovered its own rules. And perhaps that's the greatest mystery of all. Not why the universe exists, but why we're here to wonder about it. What comes next? What lies beyond the edge? What waits after the final star fades? We don't know. We may never know, but we keep looking. We keep wondering. We keep reaching toward the unreachable, because that's what makes us human. That's what makes us alive.